Okay, we're gonna do this problem just by brute force. So extension x. Um, Now we're gonna change it to logical operators. So m. We're gonna get rid of that negative sign. This should be m. Okay. We're now going to break the if and only if. Alright, so intro t, well, what is happening? Intro t, htf, hang on, there's a mistake here. What am I doing? Intro htf, and the next one is going to be t, and then we're going to htf2, and then we're going to rewrite m. Okay, I think at this point it's just some logical operations. So we're going to have h3, which is going to be htf applied to t's complement. Okay, and we're going to apply this to, can we apply this to htf2? Great. And we want to just, h3 is basically what we want. So rewrite mem comp if at h3, push neg at h3, and then exact h3. Okay, other direction of the if and only if. So intro htf t, and then htf2, and it should be the same technique. So have h3 be equal to htf. We want to apply it to t complement, I think. And this is basically what we want. Rewrite that, and then we want to rewrite. Okay, and then we want to do and apply h3 to h2. Right, and then we want to do a rewrite mem compo if and only if, and exact. Okay, so we solved the first problem. 7 more to go. Okay, problem 2. So once again, we're just going to brute force. Actually, I'm going to clear up a few more things first. So mem comp if, and then let's get rid of this also, and get rid of do this. Okay, I think that's all we can do right now for now. So we do this. Now we have 2 directions. We're going to call this htf. I'll call this t. I can't do another one. Hang on. Intro. Can we break this apart? Wait, we cannot. So we'll do this. And we'll break it apart via our cases. HTF. I'll close W. We'll close W1 and HTF W1, HWF2. Okay, so now we're going to apply this W, and we want to do rewrite mem set of. All right, and wait, I made a mistake. I think we want to do this with that. This looks better. How do we do this one? This one is going to be. This one's going to be rewrite compo. And this one is going to be just rewrite man compo if, and this should be exact. Okay, so that was one direction. Now let's do the other direction. Okay, we can't do that. Let's break this apart. And let's break this apart into this. Okay, so now we are going to do an apply this intro, and probably going to apply to T. Apply to W. Nah, W complement. This looks right. Apply and dot intro. So we have this one here. This should be rewrite HWF mem set of at HWF1. Exact HWF1. This one here should then be rewrite m compo if at push meg and then exact HWF2. Okay, so 2 problems done, 6 left to go. Okay, problem 3. So we're just going to chase these 2 definitions because there's nothing else we can do. Okay, and we're going to break this up into so now that we have an element of F, we're just going to stuff it into this. And now that we got an element of G, we're going to stuff it into this equation here. So now at this point, we note that F and G have to be the same. So plus F equals G is Hg2. This one is H3. Alright. So now that we're equal, we're going to apply G, but yeah, let's just apply G first. Apply. And G belonging in F. So G belongs in G here, and then G belonging F becomes the rewrite of that. So rewrite H4 at HF1. What just happened? That's not what I wait. What? Rewrite H4 at HF1. Right? So G belongs in F and G belongs in G, and we should be done. So apply and dot intro HF1 HG1. Great. So 3 done. 5 left to go. Problem 4. So the key idea here is that we're going to brute force this by picking an element that belongs in this part here and then shoving it through this equation to get that it belongs in that element in some setting H, and therefore it belongs in that. So we're going to take an X from this thing here, send it through these two parts to get something in H, and that'll prove it. So EXTX intro X. Mem inter if hey, I always do this. F union this does all of it. Okay. No, it's missing one. This intro. Okay, this does all of it. We're now going to intro this as HF and HG. And we're now going to break apart HF because it has an exist sign. And we're going to take this belonging in this thing here and put it through that. So our cases H1 plus F and HF1. And we're going to call this, so there's two terms here. So we'll call this with G, HG1, HG2. Okay, and I think at this point we're going to take this F intersects G and use it as an element. So apply exists.intro F cap G. And apply and dot intro. So this is going to be HG2. This part is going to be in and dot intro. X belonging F is HF2, and X belonging in G. Wait, what? It's going to be HG of HG1. HGG of HG1. Okay, great. So 4 done, 4 left to go. Problem 5. I think this is just plain brute force again. So I always make that mistake. that one, yes. Okay. Is there anything else? Okay. Alright, we can split those apart. And right, so we're going to break apart the HXF first. Okay, now that we have the thing here though, we're going to I think we're going to just alright, and let's see if we can make this work. So X belongs in F, this is just HF2. F belongs in F and G, this one here. This one here is HF1. And so by cases, HFG, F in G. This one here, we're going to have H3 equals HXG applied to F HFG, giving us this, which will then apply to HF2, giving us false. And if we have false, we can just do fact false dot eliminate that handles that, right? Yes, I think that handles it. Alright, so now the other case, and this is going to be exact HFG. Great, so 5 down, 3 left to go. Okay, so problem 6. I think this is by far the most tricky problem in the entire tutorial so far. I've solved this problem 2 or 3 times separately, and I still don't feel that I have a very strong grasp on it. The basic idea is that we're going to do proof by contradiction, and then we are going to construct a term that belongs in here, but does not belong in here. And alright, so let's get started. Intro X and intro HXFG. Okay, so we're going to have X belongs in this term here is something we want to prove, and I made a mistake copying and pasting. We also want to prove that X does not belong in this term here. And we do that by here. So actually, let's do that first. So we're going to have H2 X not in this term here. This is by far the easier part of the proof. And the key part of the proof is we're just going to invoke this part here. So let's do rewrite mem inter if at HXFG. And then we're going to do, so this term here is basically it. We can do a rewrite mem, well, member compl if. We're going to do a push neg. And then we're just going to do exact hxfg dot write. Okay, so that's the easier part. We proved it does not belong in this term here. And now the harder part is proving that it does belong in this term here. And unfortunately, I don't think there's much we can do besides just brute force the whole thing. So rewrite mem s union. Why is it saying sorry? Oh. Okay. And we're also going to our cases hxfg.left giving us a f, hf1, hf2, right. We should now do this, and I think we're just going to use exists. What do I do here? What do I do here? Right, I think that if we have f belongs in G complement, we're done. F and pick a G. I think that's the right approach. Exists, intro, okay. Why does it get more complicated? Hang on, I'm doing something wrong. I have to prove by contradiction. Oh, sorry. In this lemma, I need to prove this, and then afterwards, I need to prove by contradiction. Okay. So inside this lemma, we're going to do apply and.intro, something gets this. Okay. And then this thing here is going to be an and.intro hf1 of something else. Alright, so we need to show that f belongs in G complement. And I think the trick are these two statements here. So x does not belong in, so let's just do this. Let's see what happens if we just rewrite mem compo if and only if at h2. Push neg at h2. This is not the contradiction that we need. Huh. Alright, screw this. Um, where are we? Right, we're just gonna brute force this. If I case this, H3, F belongs in G. Right, two possibilities. So, if F belongs in G, what do we do? I'm confused right now because one of these two statements is going to give us a contradiction I want, but it's not obvious to me right now which one it is. If F belongs in G, then F belongs in this thing here, then F does not belong in the complement. This is not a contradiction. If F belongs in G, F belongs in F, F belongs in G, so F belongs in this thing here. This one would give us a contradiction. Okay, how do we get the contradiction? We're going to somehow invoke HXFG2. Rewrite. Why can't we do this rewrite? By contra. Okay, I think we're almost there. Okay, so this proves that one lemma. Now we have to prove the main thing, which should be relatively easy, because alright, I have terrible naming. I call that H2. I should call this H3. So, because of H2, we know that it does not belong in this term here, and because of H3, it does belong in this term here. So it should be relatively easy to get it false. We just want to apply H1, and it doesn't let me do that. What if H1 okay. H4 is this. Um, and now we're going to use this part here. So let us do okay, that solves it. Not a very clean solution, but I think this is the most tricky problem in this entire set. So 6 done, 2 more left to go. Okay, problem number 7. This is a relatively straightforward one. We can just brute force it. So intro x and intro hxf, hxg. Let's extract something out of the hxf. So our case is hxf with x, hf1, hf2, this is called f. Right. Now we're going to rewrite the g. So our rewrite if okay, and then push neg. Okay, now we're going to use this and extract a g out of it. So our case is hxg with. Okay, and now I think we can actually start working on this problem. So we're going to do apply this intro f cap g and apply and intro. HX. Okay, this is cap, not this. HF1, sorry, HF2 and HG2. Right, so this is x belongs in F, which is a HF2, and then G, which is I hope this cancels. I think this cancels. Okay. So now we're going to do rewrite m setup, and then apply this.intro f. Apply n.intro hf1. Apply this.intro g. Apply n.intro hg1. And then RFL. Okay, 7 down, 1 left to go. So this here is the last problem in the set theory section. I wish I could say there's something intellectually nice about this, but it's really nothing more than just a lot of mechanical grinding of the terms. So here we go. The hint is that have H2. And from this point on, like, I wish there was an elegant solution, but it's just grindy. And there's, like, nothing that I can really say about it. So we copy this part here. And now we're going to disprove it. Maybe we can do something better this time around. Nope. I think this continuous grind. Okay, never mind. Yeah, I don't think there's anything else to do here. Why is this not working? Oh, rewrite. Yeah, I get confused on when to use rewrite, when to use apply. What is going on? Why can't we do this rewrite? Rewrite. What's going on? Why can't we do this rewrite? Oh, wrong direction. Okay. This is not right. This UI is very finicky. Wait, this is one direction. So now we prove other direction. I think we just use. Okay. Yeah, let's just do this in two parts. The first part is going to be last part we're going to do okay, so this proves this theorem that we wanted, and now we're just going to continue grinding this. Um, wait, why is this not done? Did we wait, yeah, something finicky with the GUI. I think I have an extra command or something there. I believe the issue with that having this RFL. Yeah, okay, that's why. Alright, so this concludes the set theory section.